Hello, welcome to the session about Quercus, about Reactive, and why we made Quercus Reactive, what it brings to you as users to have done this shift. My name is Clement Escoffier, it's written in my back here, so it's probably me. And I'm working at Red Hat. I'm doing all sorts of reactive stuff at Red Hat, Vertex, Quackers, and a lot of other things too, SmallY and so on. And we are going to see a little bit why we did them that way in Quercus and things like that. So who heard about Quercus? Wow, that's a lot of people. That's cool. So for people that didn't raise their hand, Quercus is a Java framework that has been tailored for cloud native. But you can say, well, but Java is already cloud native. I heard that a lot. Yeah, it's not too bad. And when a French guy says not too bad, that means it's already pretty good. But we can do a lot better. And the issue is Java has been designed 25 years ago. And 25 years ago, the world was just completely different. And the thing is, it was really designed with a lot of dynamism, a lot of things that could change at runtime, like deploying new jars and things like that, the class loader thingy. So it's pretty cool, but doesn't really fit in the world we're living right now. And actually, all those features have added a lot of loads of memory usage, of startup usage, for not something that is compelling in the two things we are targeting here, microservices and serverless. Why? Because microservices, instead of having one monolith somewhere, you now have a dozen of them. And for each of them, you are going to pay the price of the JVM, the price of all the frameworks you're using. Because the JVM is one thing, but all the frameworks you're using, like Hibernate, like Spring, and so on. So the memory usage is pretty key here. It's critical. The second thing is serverless. Well, function in Java. If a function takes more than 10 seconds to start and run in less than a second, you are going to pay for 11 seconds. That's a little bit wasting your money, right? You really want to pay for only a very quick startup and executing the function. Quercus will help you reducing the memory usage, but also the startup time, really drastically. So Quercus is based on 4 pillars. The first one, developer joy. It's always hard to say developer joy because generally we all say my API, my framework has been designed for developer because I'm a developer, so I design it, and so on. It's really hard to try to project yourself as a developer using your API. And what we did with Quercus is really making this shift, saying, okay, as a users, what would really make me productive? And actually, we have a very nice hot reload. We have lots of new APIs and things like this, and you will see it live. It's really fluid. Then it's Supersonic, Subatomic Java. It starts very, very fast, and it's used not a lot of memory, really a lot less than regular thing, and it's Java. So how we did it? A Quercus application can have 2 outcomes. One is a jar, what we call a runner jar, so you run it on your OpenJDK or whatever JVM you use, and it will run fine. And already in this mode, we are going to see that we have memory gain and CPU and startup time gain and benefits. You can also build your application as a native executable, as something that includes a JVM and only the bits of the JVM, only the bits of your code that are required. And in that case, well, your memory is nothing because we remove all the things that you don't care, and your startup time is really, really fast. The third pillar is about library and standards. So again, I will ask you to raise your hand. Who use Spring? Who use JAX-RS? Or EE in general, Java EE in general? Who use Camel? Who use Vertex? Who use Hibernate? If you raise your hand, I have a good news for you. You can immediately update your LinkedIn profile and add 5 years of experience with Quercus. That's pretty nice, right? We released Quercus in February last year, and a few weeks later, there is a recruiter that say, we are looking for a developer with 5 years of experience with Quercus. And we say, seriously? Even the team doesn't have 5 years of experience on Quercus. So. But actually, it makes a lot of sense because we have reused all those libraries just mentioned. So it's not going to be something completely different. You will really find, oh, yeah, this is what I was using before. The only thing that Quercus is doing is making it the Quercus way. And finally, and that's going to be the topic on this talk, is how we unify imperative, so regular code you do generally, and reactive, and why it means, and what kind of superpower it's going to give you. Okay, reactive. Well, over the past few years, everything jumped in the reactive train. The trick is, it's very hard if you are not in the landscape to really understand what it is. And if you start Googling, you will find reactive manifestos that define reactive systems. Then it uses asynchronous communication, so you need a programming model for this. That's what we call reactive programming. You need reactive streams for the back pressure, and then you have reactive extensions that define a lot of APIs with plenty of operators, and all those reactives are associated with different concepts, going from spreadsheets to messages to elasticity. Yeah, mention spreadsheets. Do we have any manager here? I like this conference. Cool. So, yeah, but actually, if you're a manager, if you use spreadsheets, you're actually a reactive developer. It's kind of weird, but yeah, it's like it. So all those reactive bits are slightly associated with different concepts. So it's very hard for when you are not in the reactive space to understand what reactive means. And actually, none of them really tell what reactive means. So let's look inside the dictionary. And if you open the Oxford Dictionary, it's available online, and you search for reactive, you will find this. Reactive means showing a response to a stimulus. Good. Doesn't mean anything, but fuzzy. That looks pretty good for software, right? Second thing, it's acting in response to a situation rather than creating and controlling it. And this definition is actually very interesting for us, because we can apply this definition to software and say that a reactive application is an application reacting to stimuli such as user inputs, messages, failures, and so on. And then you say, well, Clement, this is the nature of software. Well, when you do a keystroke on your keyboard, you really want to have this keystroke on your screen or something like this. So it existed. It exists for a long time, and I agree. And actually, it's even slightly more sneaky than this. This could be named event-driven. Ah, this guy here. So yes, being reactive means being event-driven. That means that your piece of software, your application is going to handle events, messages, failures, and so on. So it existed since a very, very long time. The thing is that the reactive trend has changed a little bit how we handle those messages and so on. Because the number of data you need to handle, the number of requests, even if you do an internal web page in your companies, it's a lot more than what you had before. And the trend in the Java world is to use non-blocking IO for this. And non-blocking IO is going to give you lots of benefits in terms of concurrency. So how it works? Well, in the Java world, there is one library that is dominating the NIO scene. It's Netty. Netty is amazing. It's an amazing library. And this library really deals with all the IO things. It's so amazing that it's very hard to use if you are really not a network guy. So there is plenty of reactive frameworks, reactive toolkits that have been built on top of Netty that will simplify it. What it means? It means that actually Netty is going to use a non-blocking approach, meaning a very low number of threads to handle all the requests. That means that the same thread is going to will be able to handle multiple concurrent requests at the same time. So if you are thinking about thread locals or something like that, forget about them. It's a big change here. So even if we have all those reactive frameworks, at your application code, this model will be reflected. So you need to use callbacks, you need to use reactive extensions, reactor, or things like that to develop a non-blocking applications. Because if you block it, then you are going to block one of the few threads that is managing the I/O, and instead of having an increased concurrency, you are going to kill your applications. So you must never ever block. And that's actually one of the things about reactive. It's not only event-driven, it's managing event in a completely non-blocking way. So if you're thinking, yeah, I can do that using multi-threads, we're going to see in a minute why it's a really bad idea, especially in the cloud. But do we have any developers that has done some reactive code before here? Yeah, a few of them. You're using map, flat map, or reactive extension, or reactors, things like that? It's very nice. The tricky thing is, why do we pay this complexity? Sometimes you have this big code and say, oh, what does this thing doing? And actually, there is a reason behind it. Do you remember that inside computers, there are CPUs and memories? Yes, even on the cloud. That's something that we try to hide, but yeah, even on the cloud, even your private, hybrid, public cloud, there is CPUs and memory somewhere that are going to execute your program. And yes, we need to be nice with them, because that's the ones that are doing a lot of the work. Who is using containers today? Wow, lots of people, that's cool. So, containers, there is a big lie about them. I'm sorry to tell you like this, it's not really made to isolate your applications. No, it's doing a very bad job at this. It's actually made to save money. How? By increasing your deployment density. That means on the same set of CPU and memory, your container host, you will be able to run multiple applications. Okay. But if one of your applications that has been containerized is using a lot of memory, a lot of CPUs, then the other applications get less CPU and less memory, so will behave more slowly. So you may be able to troubleshoot one application and you say, I don't understand why it's so slow. The application is not slow. The thing is that it just don't get enough CPU because there is a one big bloated application there that is using all the CPUs and so on. What's the relationship with threads? Well, in the traditional Java world, each request is handled by a separate thread. So it's very easy to reason about this, but it has a hidden cost. Because if you need to handle, I don't know, 400 requests at the same time, you need 400 threads. Each thread costs around 1 megabyte of memory. So it's already 400 megabytes, not including the classes and so on and so on and so on. Well, that means that these 400 megabytes are not going to be able to be used by the other applications because it's used by this application. It doesn't really work. It has a second cost, is that more threads you have, more time you are going to waste doing doing context switches. You are going to use CPU cycles for nothing because context switches is not about your execution logic, it's really about switching threads. Even if it's been optimized over the year, it's still a lot of cycles that you are going to waste that way. And again, if you want to save money, you need to be careful with this. So you can say, yeah, but Clement, I'm using Kubernetes. Who is using Kubernetes here? OpenShift, Kubernetes, or, oh yeah, not bad. You can say, we found a solution, we are going to use quotas. Good. What happens when a container reaches quotas? It gets killed. Boom. Dead. When it happens to you, as a developer, what do? You increase the quotas, right? We all did it, I did it. It failed, not enough memory, don't worry. 200 megabytes, boom, done. Tricky thing is that doesn't fix the issue. The issue is that the execution model of this specific application doesn't really made for container and for the cloud, or you need to invest more inside your infrastructure, and that's expensive. So, what do we do there? Well, there is another trend that arrives here, is that in addition to containers, to Kubernetes and all these things, we want to build distributed systems. Call them as you want, serverless, microservices, distributed monoliths, they're all about distributed systems. And if you look on Google and say, okay, how do I start to build distributed system, there is a high chance that you will start doing HTTP-based microservices because it's simple. You start, you have your HTTP, your controllers, your JAX-RS resources, it works, and so on, and you say, hey, I've done my first microservice. Good. Then you do the second one, which we'll call the first one. Hey, I have a microservice system. Right. If you did microservices, it's for one reason. You want to increase your agility. That means you want to be able to deploy more features in an independent and completely standalone way. And you just did the opposite. What? Well, because it's not because you use HTTP that you believe that you have some kind of loose coupling between all your components in terms of, I'm using JSON, for example, so It's not coupled, it's just some objects that are serialized to JSON. The coupling does not come from here. The coupling comes from time. Basically, when you're using HTTP, you have uptime coupling, meaning that if one of the guys here die, then the caller is going to handle the failure, and the caller is going to handle the failure, and so on and so on and so on, until you get a sad user. And you don't want sad user. Because today, when I'm using a service and it doesn't work, I'm using another service, and you just lose the customer. So you can say, well, but no problem. Come on, Clement. You're living in France. It's not the dark age there. Didn't you hear about Netflix? Of course I heard about Netflix. Netflix is the best, is a secret weapon when you are working from home and the school is on strike. I have a daughter. And strikes in France happen a lot, so Netflix is great. And Netflix has something called circuit breaker, Hystrix actually. Because they didn't invent it, circuit breaker, they just really make it popular. And Hystrix is really nice. Tricky thing is that it's very hard to tune. Because the circuit breaker is going to monitor an interaction between two microservices and decide if you need a fallback, if you need to call another service, all this silly. The thing is, typically, it is configured with a timeout. Like, how many times I wait, how long I wait until I decide that this service doesn't work anymore. If you start your application and you are in this topology here, you say, okay, then no problem. I will say that this interaction here, between this one and this one, should not take more than 1 second. Fine. Except that one of the fallacies of distributed system is the topology is going to be dynamic. And it's even more true on the cloud, meaning that this service here, you can have one instances, you can have two instances, you can have one instances on your cluster, one instances in another region of your cloud, or something like that. So saying that the timeout is 1 second doesn't really work, because you need to adapt that one dynamically at runtime by doing monitoring and things like this. This can be very, very confusing and very, very complicated. So use circuit breakers if you really have to use synchronous interactions. But if you don't, well, you should not use circuit breakers, you should do something different. So what is this difference? If we apply the idea of reactive, the idea of event-driven, not to the single microservice, but to the whole system itself, we have something that we call reactive systems. Reactive system has been defined by the Reactive Manifesto, and basically it's an architectural style to make distributed systems that works. And it's kind of cool, right? We really want to build something that works. So the idea are actually very simple. You say, yeah, that's just common sense. We are going to use asynchronous message passing between all our components. That means that we are going to send messages. Those messages are sent to virtual addresses. And because these addresses are virtual, you don't know if there is 1, 2, 10 consumer behind it. And this number of consumer can evolve over time. You can scale up, scale down, and decide what you want to do. That gives you elasticity. Simple. Because you can have more than one consumer, if one consumer dies, another one can manage the message. And depending on your message-oriented middleware you are going to use, most of them have acknowledgement and very complicated things in terms of resilience. So you can really build a resilient system that way. If you're able to handle the load, the request, the event, even under fluctuating load, and even when facing failure, you become responsive. You are building a system that's actually going to work. Yes, failures will happen. And bigger is your microservices system, bigger is your distributed system, higher the chance that it doesn't fully work completely. And that's fine. Failures are part of the game. You need to take these failures into account and make them really a first-class citizen, designed with failures in mind. That's what this manifesto is all about. Okay, so I already mentioned we're going to use messaging. Fine. But that exists since more than 25 years. I really need to edit this slide because it's probably more closer to 30s now. Messages and message-oriented middleware, Kafka, Pulsar, and so on, are going to use non-blocking message pacing. Good. That check one of the boxes we had initially. It will manage elasticity, as I said, and resilience. But you can go even further. Because the world, in terms of amount of data that is collected, has completely changed, we also need new patterns. The first one is message streaming. we need to be aware to react to new messages in a very quick way. And I was discussing with an engineer of Michelin, they do tires in France, and they were telling me, well, one of the revolutions we have seen over the past few years that before, to get a report, we had to wait 1 day. Today, we just refresh the browser. And I was telling him that the WebSocket was probably broken because you should not have to refresh that. Anyway. Second thing, you will still be able to use request reply. Just, it's going to be completely asynchronous and maybe timely decoupled. And that's pretty nice because if one dies, no problem. It will still be there. And finally, publish, subscribe. Publish, subscribe, very old pattern, right? We all heard about that. But actually today, in the microservice world, it's a key pattern. Because you can have all your messages flowing around your microservices, and you want to add a new one, and you don't need to call those other microservices. You can just read the same set of messages and say, oh, this is what happened. I can do this now. So you can really extend your microservice system by just observing the messages that have been emitted by the other microservices. You can't do that with HTTP. You can't do that with end-to-end or one-to-one communications. I didn't mention too much Quercus here. And I'm going to explain how Quercus works and why we made it reactive now. So first, Quercus can be seen, and this is going to be very weird, as a build tool. Because the idea of Quercus is to take your frameworks and to move all the code that could happen at build time. So, some example. Let's imagine Hibernate, because Hibernate was quite popular here. Hibernate, when it starts, is going to look at the persistent.xml file. So it's going to look at the file system, scanning, oh, find it. To read an XML file, you need an XML parser. Xerces. Awesome, right? Who loves Xerces? Oh, no one? I don't understand that. Xerces was great. 10 years ago, maybe more. Xerces is huge, really huge. I don't even understand how they reach this level of complexity. Well, XML is complicated, actually, so that may explain it. Then, Hibernate, once you add this, it will scan for all your entities, so looking for annotation and things like that, and build its own model of his world, the Hibernate world. This entity is going to this database, and this table, and so on. And then, when all this is done, it will start running the thread, configuring the connection pool, and so on. Everything till starting the thread can happen at build time, which means that the persistent.xml file is going to be checked at build time, not at runtime, which means that you can save Xerces at runtime. So no more Xerces in your library, in your package, because yeah, it's done already. All your entities and so on already managed, already scanned, so no more reflection, no more annotation scanning. And that way, we are saving a lot of memory, because less classes, and we are much faster to start. The secret of Quercus, less memory and start faster. As I said, Quercus can package your application in two modes, Java, and then you run it on your JVM, or native. Because at the same time, because we have all this knowledge about your classes and applications, we can configure a specific compiler, which is a GraalVM compiler, to build a very tailored executable for your applications. And this executable is going to just have enough of the Java class you need, the bits of the JVM you need, and so on. So it's very, very small, very, very fast. But what about reactive? Well, as soon as you do Quercus, you are going to run on a reactive core. Yes. That means that the core of Quercus is actually completely reactive, meaning it's going to use a low number of threads. And when you get an event, a request, and so on, it will go through a routing layer and decide who is going to handle this request or this event. So if we found during this routing layer that it was using a servlet or JAX-RS or a Spring controller, no problem. That's imperative code. We are going to switch to a worker thread. And then you say, yeah, but you mentioned that thread pool are bad. The thing is, they're still bad. But we can reduce their size because you also have all the other possibilities. And if you realize that some routes, some endpoints, some message processing is really called a lot, and actually is non-blocking, then just use a reactive route, or reactive messaging, or reactive data access to write to a database. That will save a lot of threads, a lot of CPU cycle, and a lot of memories. That's how it works. So in addition to startup time, to a memory, we can actually save CPU cycle and even more memory because we reduce the number of threads. So how it works? Well, very simple. You can have some reactive HTTP servers. That will be the Quercus one. Quercus is based on Vertex again, so it's going to be the Vertex HTTP server. And then we have this routing layer that will decide who is going to handle this request. For those who used Vertex before, this routing layer, there is no secret, it's Vertex Web. Simple. And then we find the application code, we call it, and so on. And this code, imperative or reactive, can emit a message, an event. And this event is going to be sent to a channel and then routed to the messaging part of Quercus that will decide what to do with the message. And maybe this channel is mapped to some external messaging middleware like Kafka. And on the other side, the same thing. A Vertex bit is going to receive these messages, go through the routing layer, go to the application code, and so on. So basically, with Quercus, you can do HTTP, you can do messaging and streaming in one stack. And why? Because it's all reactive at core. But if you're a Java guy, if you're a seasoned Java guy, when I mention messages, you say, come on, GMS. Who used GMS? So, I love this phrase. Yeah, I used it. Try this. Like GMS and Corba is kind of the most hated technology we used in the Java world. And yeah, it's an asymmetric API. There is plenty of things that we don't like. So we tried in Quercus to make them easy to consume, easy to send events, easy to consume events, easy to process events. Again, developer joy. And to illustrate this, we are going to go through this demo, which is a reactive coffee shops. You can find all the demo on this GitHub URL here. And basically, I will explain how it works when you go to a bar in France. Generally, you go there, you go to the bartender, you pay your coffee, he will go to the coffee machine, he will prepare your coffee, go back to you. Don't say thank you or hello or anything, it's France, so that's normal. But during that time, all other customers are queued, and they are not being managed. There is a new type of coffee shops where you go there, you go to the bartender, you say, okay, I want this. You pay, they will get your name, they will misspell it, that's part of the brand. And then they will tell you, hey, wait over there. Okay, fine, but eventually you get your drink, right? But during that time, while you were waiting, other customers were able to be managed by the bartender and so on. So it's much more reactive, much more non-blocking from this point of view. Yes, me as a customer, I waited. I've waited my beverage because it takes time to be prepared. But the other customers have been handled at that time. This demo is going to use Kafka because, well, if you don't use Kafka today, we all want to be hipster. Same apply to plenty of technology we support, like IMQP, like Azure, Event Hub, or Google GCP has its own messaging, PubSub, sorry, even on Amazon SNS. So let's switch to the demo. So this is my coffee shop here. Let's check that it's running, and I'm going to order my coffee. Oh no, it's the HTTP one, so it gets spelled correctly. And I want a cappuccino. It's called it, and during that time you checked it. I was unable to order another coffee because it's blocking. But as I said, one of the issues with HTTP is the uptime coupling. So if I stop this barista and I order a new coffee, boom! Of course, no one there to serve my coffee, which is very, very bad because I really need a lot of coffee. That's for your own good that I drink coffee, or I'm really in terrible mood. So if we switch to messaging, then yes, I get my name misspelled. So when I say Clement, I generally ends up with John. Don't ask. And let's get a latte here. So I can order my latte. Oh, doesn't work anymore. Let's retry. John, Oh, let's ask for a cappuccino. And it doesn't work, so let me check why. Oh, yeah, forgot to write the code. The system is running, but I forgot to write the code. So remember what I say about the live reload here. That's what we're going to demonstrate right now. So to send an event, I need an object to send an event. I'm going to use an emitter. Oh, by the way, you recognize this API here? Right? This is Spring, right? That's the compatibility layer of Quercus to use Spring API directly in a Quercus applications. And here, I'm going to use auto-wired, okay? And I'm going to inject an emitter on a specific channels, which will be orders. And this channel, this is an emitter, yes. And I'm going to send order to this order emitter. And I'm going to do the same thing for the queue. I will explain why. I want beverages, and I want beverages. Beverages. So why do I'm sending 2 events and not 1? When you go to such kind of coffee shops, there is something that really makes me mad is people behind me in the queue get served first. It happened to you, right? There is absolutely no, it doesn't make any sense, right? So did I forget it, and so on. So we're going to also have a dashboard that will tell us that our beverage is really under preparation and so on. So it's actually for my own sanity. So now I'm going to say that the beverage is in queue. Okay. And here I'm going to send the orders to the barista, and that's it. I go back here, I refresh. Yeah. Clement, like this. And now, oh, now it works. And now I can place a lot of orders at the same time. And what we see is that they're in queue, and then they get processed, eventually. Yes. And we have one barista here. It's named Leo. Nice. But, you know, Leo sounds like a little bit of French name, actually. So Leo can also decide to, where it is, sorry, my terminal. Not this one, here, yes. Take a break. And here, I still want some latte. I want a lot of latte. But here, the difference with HTTP is that it's still working. It's just no one is there to prepare my beverage, but as soon as someone is going to come, it will be prepared. So if I go back to my terminal, and I start another barista, Kafka barista, oops, it's going to process it. These Kafka baristas are started in 0.0.18 seconds. Why? Because I compile it into native. Because all the code you do in Quercus, using Quercus extension, can be compiled to native, and it will start like this. So if I go back here, yeah, Ava got my latte, my lot of latte there. Pretty nice. So what happens if we have a rush hour and we have both a barista? So where is my second barista? Here it is. I'm going to restart this one too. And during that time, I'm going to order espresso. A lot. Lots of espresso. Really a lot. So that's rush hour. Like everyone in this room going to this coffee shop. And here, we are going to see that now the load is splitted between the 2 baristas. So it's not evenly splitted. There is many things you need to know about Kafka, how to do this, because again, that's use Kafka. But basically, that gives you the ideas. So I didn't really show you the code of the barista, right? So the barista is actually very, very simple. Here it is. That's all. 2 new annotations. The first one say, I'm going to get messages that are transiting on the orders channel. And I'm going to process them, and the result is going to be sent to the queue channels. That's it. Here I've decided, because preparing coffee takes time, that I'm going to use an asynchronous method, but we support more than 30 different signatures, going from the synchronous one, get 1 element, return 1 element, to something really reactive. You can get streams, join streams, and do things like this. So you really have a choice, so you can decide which signatures fits your need. Here I just decided to go for this one. So that should be fine, right? At channel, at incoming, at ongoing. 3 annotations, and you get the full spec, more or less. Because this is part of a spec, which is named Microprofile Reactive Messaging, that has been released 1 year ago. And we are preparing a new release for June-ish. Yeah, maybe June or September. We will see. But yeah, more or less it's this. What I didn't explain yet is how these channels have been mapped to Kafka. Well, this is done in the application properties file here. Typically here, I just say, well, my channel's orders is associated with the connector small y Kafka, meaning that is going to be the Kafka connector provided by small y. There is other connectors available in the market, like if you use OpenLiberty, there is an OpenLiberty one, I don't remember the name, it's probably OpenLiberty-Kafka or something like that. So that means that this channel is going to be managed by this connector. And then you configure the connector. So if you're used to Kafka configuration, you say, okay, so this is my codec, and this is my offset, so you can configure all your Kafka things here. But your code, remember, your code doesn't care. Your code doesn't know if it's Kafka or not. Meaning that if tomorrow you say, yeah, Kafka, Pulsar is much better, you replace the connector and you get your application up and running. That's it. Well, install Pulsar first. Actually, what I didn't mention here is that I'm running Kafka locally. I'm using a Docker Compose file, so you can check it. It's using Streamzy. It's not using any type of Kafka. Streamzy is a distribution of Kafka we are making at Red Hat that has been really made for Kubernetes and things like this. It comes with an operator and things like that. If you go with Kafka on Kubernetes, there is plenty of things that you need to know about how it works, so don't go alone. Confluent has a very nice product around that. Red Hat has Streamzy, so don't try to install it by yourself. It can be really ugly. Yeah, something for the outgoing and so on. But that's more or less it. So, just to summarize that. Okay. So we have seen that to send messages or events to channels, you just use these emitter patterns. Easy, right? You just inject it. Oh, by the way, here I'm using @inject. Because what I was doing with Spring also works in JAX-RS and CDI. You can even mix them. Actually, this morning when I was doing this presentation, I used @inject inside my Spring controller, and it was working. I was a bit surprised, but it was working. So, relatively simple, and then you use the send method to say what you want to send. Then, on the other side, you use @incoming and @ongoing to process those messages. There is another annotation which is not present here, which is @acknowledgement, and this acknowledgement lets you decide when you want to acknowledge the incoming messages. It can be before calling this method, that's what Kafka autocommit is actually doing, or after the method, which is much safer, like if I process this message correctly, then commit the offset. So yeah, there is other policies too. So that's the only thing that is not covered here. Again, we have plenty of signature here, so you can quickly find the one you want. So the board, we have seen this. We have also seen this configuration here. We try to reduce the configuration to the strict minimum, and we are making progress here. So probably very soon you will be able to just skip the configuration and we'll be able to detect it by reading your code. Because again, Quercus is a build tool, more or less. So I can look at your code and say, oh, that's what you want to send. By default, the name of your channel is going to be the name of the topic, and I'm going to try to find the right serializer or something like this, depending on what you have in your applications, and you're done. That's going to work out of the box. Yeah. We have seen this, meaning that if a barista is not there, we'll still be able to handle the request, meaning that my coffee order is not going to be lost, and that's a very good thing. So basically, we have shown here that we have the resilience part of the reactive system. Even if we are facing failure, like my barista take a break or stop processing messages and things like that, I can recover. because fault tolerance is not about handling failures, it's about recovering when you have failures, and recovering in a nice and elegant and smooth way for your users. Here, I will still get my coffee once another barista is coming. We also have seen this. If there is rush hour, you can have more than one barista that will handle my orders, and they will split the load. If you're a Kafka user, you can say, yeah, but this doesn't really work well in Kafka, and you're absolutely right, because to get this working, you need to configure your topics to use enough partitions to support this elasticity. So if you use Kafka again, you need to think about that in advance. If you're using MQ or MQP and use just a topics, then it will be managed automatically. So depending on what you use, it might be a little bit different, but for your code again, doesn't change anything. Also, your code can actually depends on Kafka, depend on Kafka metadata and so on. We allow this, it's supported. But what we have seen over the past year is that in 80, probably even 90% of the cases, you don't care. You just want to send something and receive something. How it's done? Magic. I didn't really mention reactive streams so far, but reactive streams play a great big part on this whole story. Because, so what's reactive streams? Reactive streams is a back pressure protocol. That means that you don't want to send too much to one of the elements of your system because you may kill it. And it's a good thing to not kill part of your systems, at least if you don't plan to do that. So reactive streams is a back pressure protocol that will avoid this, and how it works is that the publisher, the consumer is going to tell to the publisher how much it can handle. And all those pink, reddish arrows are actually reactive streams. But you, as a users, you don't necessarily need to care about that. The framework is going to handle this. You can, if you want, use subscriber, publisher, or Hystrix Java 2, or Reactor, or anything else. That will work too. We support that. But most of the time, you don't really want this. And lesson, don't try to implement publisher. It's very tricky. It looks simple, but actually it's very, very complicated. That's all I have. So again, with Quercus, it's a new Java framework that will really been tailored for cloud native. We really want you to have a good Java experience in the cloud. Starting fast, less memory, putting more on less. So basically, saving money. But we don't want to do that without you as developer, well, having some joy developing. And you see that? I was editing some code, refresh, there. If you use some browser plugin named Live Reload or something like that, you don't even have to refresh. It's going to do that for you. I'm not a front-end developer, so I don't ask too much about the front-end things. Well, that was the maximum I can do in terms of front-end, basically using Bootstrap. I'm still at the jQuery edge, so not everything after? No, that does not exist. With Quercus, you can have imperative. We have seen that. You can have Spring Controller, you can have Jack Serverless resources, you can have all these event servlets if you want, or reactive. You can have message processing, you can have reactive routes, so HTTP, but really non-blocking. And both can interact. As we have seen, thanks to the emitter, we can go from imperative to reactive. And actually, the opposite is also true. You can get channels inside an imperative code and read it, like doing a for each or something like that. That would work too. But thanks to this reactive world, this reactive core that we have, it lets you implement reactive systems relatively easily. So better distributed systems that will continue to work even when facing failure and even under fluctuating load. Then you can say, well, but the elasticity you showed us, you started the second baristas manually. It's because I'm on my machine, but if I will be on the cloud, I could configure an autoscaler, something like Knative or Keda, or even on Kubernetes, there is plenty of them, that will automatically scale up and down my number of subscribers, my number of Kafka baristas. That will work out of the box. And because it starts like this, if you're native, that's actually going to be very, very smooth, very nice experience. Finally, you can use data streaming, do all those reporting and so on. We even have support for Kafka streams if you are really in the Kafka world, and you can combine all those technologies together. So If you want to start with Quercus, you need to go to code.quercus.io. And then you will just select the extensions, what we call plugins, so we call that extensions that you want, and we'll generate the project and you're done. The project comes with an example, some tests, because testing is important, and Docker files that show you how you can containerize your application, both in JVM mode and both in native mode. And so you can compare and decide what you want. You can go to Quercus.io, where you will find all the documentation, the blog, and so on. And Quercus is not only disruptive on the technologies, we are also very disruptive in terms of how you interact with the team. Did you hear about Zulip yet? Who use Slack? Zulip is like Slack, except that you will have 100 times more channels. Amazing, right? That's going to be fun. The thing is that we can quickly organize all those channels, and for the team it's very easy to know, oh, here I can answer this question, here I can't, and so on. So it's very, very nice. The UI is really not great, but and you can follow us on Twitter, Quercus.io. You can also go to the GitHub project. Everything is open source, Apache license. You can even give us a star on GitHub. It's totally useless, but you know, we like that. And that's it. Thank you very much. And we have 3 minutes, 2 minutes?
We have sort of 3 minutes, maybe 4 minutes for questions.
Wow, 4 minutes for questions.
You're lucky.
Any questions?
Everything is crystal clear, I assume, then.
Yeah, here we have one. And anyway, if you have a question afterwards, you can go to the Red Hat booth, and you can actually go even to the IBM booth to see more demos, to get stickers. And if you go to the Red Hat booth, and there is a few computers where you can actually try Quercus directly, with different scenarios, from getting started to Kafka to Spring and things like that. And if you go through, you can even get a t-shirt. And they are quite good. And they arrived late afternoon. Yeah, they are there now, so you can really go and get your t-shirt. So your questions?
Yes. Does it work with Kotlin? Because
yeah, I didn't mention that. So the core of Quercus and what we really work on is Java. However, there is extensions that make it work with Scala and Kotlin. We really want to be serious about Kotlin because Kotlin is absolutely awesome. There is plenty of things I love about Kotlin. And funny thing is that the whole Quercus release process is actually implemented in Kotlin, which, yeah, that's my things. So yes, it works with Kotlin. You may have issues going to native with some feature of Kotlin, typically coroutines. We really want to work on this, and we have a student starting in 1 or 2 weeks that is actually going to look a little bit at this to see if it's possible or not. So yeah, so right now Kotlin will work, except the coroutine part, but yeah, work in progress. Yeah,
Okay.
question here.
Quercus is not only a library, you say it's also a build tool. So how does it was Graal VM also underneath?
So
This, so if I download this example application and I build it, how does it happen?
So if you download this demo, that's going to be a Maven things with a Quercus build plugin. But Quercus is both a build tools and a bit of a framework that will just orchestrate everything that needs to happen at runtime. That's it. Then, if you want to go native, then yes, you need Graal VM, the Graal VM compilers, to compile it to native. We made it very easy compiling to native. I don't know if you used Graal VM before, but the compilers is, well, like all compilers. It has 25 arguments, and the fifth one is really important one, and you necessarily need to fix it. So it's really terrible in terms of experience. Quercus, building to native, you just say Maven, package, -p, native. You just say, okay, I want the native things. It's going to take minutes, because what I didn't say is that, yeah, comparing to native is taking a lot of time. But then you get your native executable.
Okay, then the last question.
How will Quercus be available in OpenShift?
Quercus well, I'm working for Red Hat. So basically, that means that everything we do have to work on OpenShift. We have no choice, or we're fired. So Quercus works very well in OpenShift. We provide a different way to deploy in OpenShift, S2I and so on. So this you get everything covered. We also provide guidelines to build your containers correctly, because building containers is hard. It's not because you can run your application in a container that it's the right way, and so you really need to think about that. So we provide all those guidelines. We even have Kubernetes extensions that actually look at all your classes, all the extensions, and compute the descriptor, so the templates, more or less, that you need, so with health checks already configured and things like that. We want to go further and to make all this really smooth and directly connect to OpenShift. And we start seeing some results. The dev mode I'm using here, you can do a remote dev mode. So that works also for Kubernetes, Docker, or whatever, not only OpenShift. So you have your pod running, you connect to this pod, and when I edit my code on my computer...
To skip the details because...
Oh, sorry. Yes, he
time's
said...
out, but Clement will be available later on, so thank you very much.
Yeah, so if you have more questions, Red Hat booth. Thank you very much.